The diagram shows a bob hanging vertically from a string and at rest, with gravity pulling it down by mg and the string pulling up with tension T. In equilibrium those two forces are equal, T equals mg, so the vertical forces balance, there are no lateral forces acting on the bob, and the net force is zero, which is why the bob stays in the vertical position. When the pendulum is displaced by an angle theta, its weight mg is resolved into two perpendicular components, a radial component mg cos theta along the string, which is balanced by the tension, and a tangential component mg sin theta along the arc, which is unbalanced. That tangential component is the resultant restoring force that pulls the bob back toward the equilibrium position. Applying F equals ma to the restoring force gives ma equals minus mg sin theta, so the angular acceleration is A equals minus g sin theta. The pendulum does not follow SHM for large angles. For small angles, below under 10 degrees or 0.17 radians, the arc of motion is essentially straight, so sin theta can be approximated by theta, in radians. Geometrically that means sin theta x, L, where x is the horizontal displacement and L is the length. Substituting this into the restoring acceleration A equals g sin theta gives a g, x, L, so the acceleration is directly proportional to and opposite the displacement, which is the linear relation that produces simple harmonic motion. Applying the small angle approximation gives A equals minus g slash L middle dot x, so acceleration is directly proportional to displacement and points back toward the equilibrium, the defining feature of simple harmonic motion. Comparing this with the standard form A equals minus omega squared x lets us identify omega squared equals gl, therefore omega equals the square root of gl, which confirms the motion is SHM for small angles and lets us calculate the period if needed as t equals 2 pi, omega equals 2 pi the square root of Lg. Substituting omega equals 2 pi f gives 2 pi f squared equals gl, which rearranges to f squared equals 1 slash 2 pi squared middle dot g slash l. Taking the positive root gives f equals half pi middle dot sqrt g slash l. This shows that, for small oscillations, the frequency depends only on gravity and the pendulum length, not on the mass or the amplitude. The frequency of a simple pendulum is f equals 1, 2 pi middle dot square root g, l, and the period is t equals 2 pi middle dot square root l, g. Importantly, mass does not appear in these equations, so the swing time depends only on the pendulum length and the local gravitational acceleration.